material and different facts about that. And also there is some sort of uh, last year video recording is also available, and there are some sort of set of questions you can do it any number of times. So as long as you understand, that is fair. So then we discussed a little bit about the three main items available in group 3. So carbon, silicon, and germanium. And let me revise some of the things. So I'll start recording.
Recording in progress.
Now, silicon and germanium, we know that for the most of the electronic systems, we use either silicon or germanium. So initially we used germanium for most of the things. Nowadays we are using silicon. So one main thing is that it's very cheap. It's not the only reason why we are using it. It's you can get ultra high purity material, right? So germanium also ultra high purity material. And the most important thing is that oxidizing it, you can make silicon dioxide, which is a very good insulator. Want to make some device, so you take a silicon substrate and then you dope it with P and N, whatever you want. And if you want to make a tracks, like, okay, this is a conducting path. So after the conducting path or next to the conducting path, you need to have insulation path. Otherwise, all the conducting path will get connected. So therefore, we can easily get insulators by oxidizing it. So all those things you can do it one single silicon substrate. So that is the main one of the main advantages that we have in use silicon. And one issue that we have with the germanium is that once you oxidize the germanium, it's porous to water. So that water comes in, water molecules trapped inside, and also porous to hydrogen. So it's kind of problematic. So, and when it comes to carbon, one thing is it's very expensive. The other one is it's kind of very difficult to get the materials with ultra high purity, because it comes with a lot of contaminations and the band gap is very large, so that at the room temperature it really won't act as a what you call the semiconductor. So the crystalline form is diamond, you know that. So that's the reason why we don't use carbon in general as a semiconducting material. Right. So moving towards the next section. Now, let's suppose you have electric field, which is towards your right. Now let's say in this electric field, so electric field is towards your right, and we have positively charged particle. My question is now, what happened to this positively charged particle in this electric field? Will this move or remain stationary? If it moves, tell me the direction, is it A or B? Okay, good. Right? It moves towards C. There's no C. Right. Okay, so the idea of the direction of the electric field itself, if you put a positively charged particle, a force will be applied towards the direction of the electric field. So that's the idea of that. So if the force is applied to this particle, so it will start moving towards your right. So that's the idea of this one. Now, let's consider a situation like this. Now I have positively charged particle and negatively charged particle. Now tell me what will happen to the positively charged particle. Will it move towards B or A in this case? It will move towards B, right? So there's no difference because the electric field, so the electric field coming from the minus charge is like negligible. So this force will be acting on the positive charge is towards B. So it will move towards B. And what can you say about negatively charged particles? To which direction will it move? It will move towards A, right? So basically this particle will go this direction, this particle will go this direction if you have electric field in towards this direction, right? So it's as simple as that. Okay, good. Right. Now, when it comes to charged particle, free charge particles, so it could be free electrons, or it could be free holes, or it could be some ions in a liquid form. So any charged particle which are free charge particle, there are two main mechanisms available for them to move. So one is the mechanism is the drift. So this mechanism is drift. So drift happens because of the electric field. So previously we discussed that in the previous slide. So this positively charged will move towards left, move towards right, and negatively charged particle move towards left because of this electric field. So this is called the drift. And in addition to that, there is another mechanism. So that's the drift. And there is another mechanism called diffusion. So diffusion is kind of very complex this mechanism, but I can simply explain by considering simple terms. Now, diffusion happens is that if you have high concentration of the particles, though they tend to move towards the low concentration. Right? So you can think like it happens like because of the particle pressure or something like that. So it's like that. So let's say if you have some volatile material in a bottle, right? So it could be a cologne. And if you open this lid, what happens is that the particle over here, they start diffusing. So from high concentration to low concentration, right? So this is a similar scenario. So the charged particle also tends to move from high concentration to low concentration. So this mechanism is called diffusion. Is it clear to everyone? So you have two mechanisms. Drift is because of the electric field. Diffusion happens from high concentration particle to low concentration particle. Right. Now I'm moving towards some interesting device. This is called the PN junction. Right. So the way that we make a PN junction is that you take a silicon substrate, and one side you dope with a material taken from maybe a fifth column, like phosphorus, so that this side you get additional free electrons. Right? So these are free electrons. And then this side, so we call, since we have additional free electrons in this side, we call it N-type material. So the other side you can dope with something like boron, which is taken from the third group, so that you have additional holes. Right? So the crosses and the minus signs I'm putting here, those are movable particles, so holes and electrons, right? So when you make this one, so we call this is a PN junction, right? So it's not that you make N-type material and P-type material and solder it, but what you do is you take one single substrate and do everything on that, right? So then you make a PN junction. Now, so when you have PN junction, what can you say about initially, right? So this is how, as soon as you make the PN junction, this is how it looks like. So if you look at N side, what can you say about the Coulombic charge of this N side? What is the charge of the N side? Is it positive or negative? So everyone, please give me the answer. Yeah, right. Okay. So remember that. So what I have drawn here is that those are free electrons, but corresponding proton is inside the nucleus. So therefore, whether it is N area or P area, these are not charged. When you consider the average, there's no any charge. So it's a neutral particle. It's a zero charge. Is it clear to everyone? Most of you gave answer like negative. So we call this one is N-type because you have more free electrons. Is it clear to everyone? Yes or no? Right, right. So remember that although we have free electrons, the corresponding proton is inside the nucleus of the corresponding atom, so that it's not negatively or positively charged. So we just have a free electron only, right? So just keep in mind that otherwise it's difficult for us to develop the rest of the thing. All right. So this is how the PN junction formed when time t equals 0 initially, right? So we have free electrons in this side and free holes in this side. Those are the majority carriers. Of course, in this N side, you can see few of the free poles. Right? So N side also you will see. So let me put P and N here. So this is N side and this is P side. In the N side also, now you can see there are a lot of free electrons, but still there are few free holes also available in this N side. Right? Why do we get free holes in the N side? Can someone tell me the answer? Yeah, they are minority carriers because of the temperature, right? Of course. Now there are two mechanisms to have free electrons or free holes. One is the increment of the temperature. The electrons in the valence band jump to the conduction band, so that we are making a pair, electron hole pair, right? We are getting free electron as well as free holes, but that's a very small number of particles available at the room temperature. However, the other mechanism is doping. Once you dope it, you can get large number of free electrons or free holes. Now, for the N-type area, you can have like few free holes, and in the P-type area, you can have a few free electrons. Those are minority carriers in those regions, right? Now, when you look at the boundary here, in the boundary on your left, what can you say about the free electron density? Is it high or low? It's very high compared to the right side. Left side, free electron density is very high. Now, what could happen is that, so remember that the electrons are free particle, which you can move. So these free particles could move to, because of the higher density, they could move to the lower density area, right? What is that process is called? It's called diffusion, right? So these electrons could move to this area because of the diffusion. Now, remember that when free electrons moving towards this direction, what is the direction of current flow? It's the opposite direction, right? So current flow happens in the opposite direction, standard current, right? Because electrons are uh, negatively charged. And also similarly, the holes over there, they have higher density in this region, so they tend to move to the other region through the diffusion. Right? Okay, so then this is what happens after once you make the PN junction. This is what happens. Now, initially, this is a free hole. That means it requires some kind of so let me clean this. Right. So so this one, so I guess you can see my laser pointer. This one is a this one requires one electron, or you can say there is a movable hole. So you can move this hole might move here. And what is this? It's a free electron. Now, what happens if this free electron moves this side? So when free electron moves to the right, what will happen? So let's say this free electron, this moves towards right. So once you remove the electron, now the way it works is like, it's like you have phosphorus here. It's making 4 bonds nearby, and then this is one of the electrons, right? So this is the situation in this side. Is it clear? Now this electron, it could be something like this. Then if this electron moves to somewhere else, what happened to this phosphorus atom? It creates positive phosphorus ion, right? So this becomes positive because that electron is gone till it makes 4 different bonds, right? So this becomes P plus, but although it is positively charged, can we move this one? No, we can't, because it is heavy and it's in this lattice. You can't move it. So now the same thing with the hole. Now what happens is that because of the diffusion, you get negatively charged ions close by and positively charged ions in this direction. So now when you look at this one, this is really positively charged, unlike the other one. So these are positively charged ions. Now, since we have positively charged ions and negatively charged ions, we get electric field. So now what would happen is that, so when you are in this situation, so probably still left side, you don't see a lot of particles. So diffusion could happen still, right? So then this layer is increased. Now what happens is that you have positively charged particles here and negatively charged particles here. When you have positively charged particles and negatively charged particles, what happens to the system is that you are getting an electric field, right? So the direction of the electric field, right? So the direction of the electric field is from positive to negative, right? So this is the direction of the electric field. So the higher the number of charged particle you have, the stronger the electric field. Is it clear to everyone? Right. Now, let's say still, if you look at this section, you have a lot of positively charged particles. So these charged particles are tends to move to this direction because of the diffusion. Right? Now, let's see the electrons also, there are electrons. They also tend to move towards this direction because of the high density here. Now, let's assume that we get one electron, this electron, it moves here, free electron. Now, so the one process is diffusion. Right? So this electron is try to move towards right because of the diffusion. Now, when electron moves here, what happens is that we have electric field here. Because of the electric field, Now, what is the trend? So if you have negative particle in this electric field, to which direction will it go? Is it A or B? Electron has to move direction A, this side, right? Now what happens is that although because of the diffusion, although this electron want to go there, because of the electric field, it bounces back to here. Is it clear? Right. So then let's take a look at what's going on with the holes. Now, if this hole here you have higher density, if the hole is try to move here, now what happens? This one also bounce back to this direction because electric field is in this direction. When you have positive particle tends to move towards your right. So this free holes, although they wanted to go this direction because of the high density, because of the electric field, they are tending backwards here. Now what happens is that we are in a situation we can't no longer send electrons towards right or holes towards left. So in fact, what happens is that some electrons they tend to move in this direction at the same time. Some of the holes tend to move this direction at the same time. Some of the holes are moved here. So actually, when you have this situation, we are in a dynamic stability. We are stable. This electric field is not growing. So this is the region we have the ions. Electric field is not increasing. But diffusion is also not increasing, but actually happens is that some of the electrons, they are moving towards this direction. At the same time, some of the electrons are moving in this direction. So the total, the resultant one is zero, right? So this is called the dynamic stability. So that after a while, so initially the system, looks like this. After a while, you get a region like this, and this region grows. And this region growing is stopped by the region itself because of the electric field, right? Now, what can you say about the movable charge particles available in this region? This section and this section, do we have any movable charge particles? Yes or no? No, we don't have. These are charged particles, but those are ions. You can't move them, right? However, there may be some positively charged particles, negatively charged particles in this region. Those are minority carriers. And also some negatively charged particles in this region. Those are minority carriers, the thermal electron holes pair. But those are very small numbers, right? So just keep in mind that there could be some minority carriers, but in general, there's no charge particle, free charge particle. So therefore, this region we call depletion region, the region where you can't do the charge transportation because there's no charge carriers. Right? So this region is called depletion region. And this electric field, the strength of this electric field is depend on the material. Now, if it is silicon, this electric field is 0.7 volts. If it is germanium, this electric field is 0.2 volts. And this electric field is sometimes we call barrier potential, the potential that acts as a barrier. Right. Now, this is the same thing given in one single picture. So this is time t equals 0. You have in an p-type material, then t equals in between you get some positive and negative ions, and after a long time period you get a depletion region develop, and you get electric field in this direction, and you are in the dynamic stability. Right. Now, so we discussed the barrier potential as well. Now, when you consider the situation, we do something called biasing. Biasing is applying external electric fields and current to operate certain devices. Now here, when I refer bias, it's a supplying of voltage. Zero bias is that I have not supplied any voltage. The situation is just like that. So this is a PN junction, and it remains as it is, and you have electric field. Because of this electric field, you get a barrier potential, some voltage. So it's 0.74 silicon and 0.2 for germanium, right? So this is called zero bias situation. Through this junction, at that time, no current flows through. And then we can do is we can try to bias. Now, here what we have done is we have applied external electric field using a battery, right? Now, the electric field of this one is in this direction, right? From positive to negative. This is the electric field from the barrier or the depletion region. Now, by applying a battery, so positive terminal is here and negative terminal is here. So the battery electric field is also from positive to negative. So this is the positive terminal and this is the negative terminal. So you have this electric field from the barrier, the default one. Now you apply another electric field in the same direction from the battery. Right? Now what happened to the total electric field? They are getting sum up, right? So the total electric field is E bat plus EB. So you get large electric field. So in other words, you are getting large depletion region. Right? So biasing our devices in this mode, we call reverse bias mode. So the N-type material is supplied with a positive charge. Now what happens is that depletion region is increasing or it's expanding. And so since you have large depletion region, basically no current could flow through this one. However, there may be some minority carriers. Now, for example, if we have a free hole here, this free hole will be moved towards right. Is it clear? If somehow if we get a free hole somewhere here, that will be moved towards right. And if we get free electron somewhere here, that will be moved towards this direction. Because of those charge particle movement, there may be extremely small current flowing through this one. That is what we call leakage current. Otherwise, there's no any current flow through this region. And this is kind of like a area where there's no any thing to handle or any charge free charge particle to move here and there. It's like this region is like some sort of insulator. Is it clear? The reason why I say insulator is that if it is a conductor, you need to have mobile charge particles. So if you don't have mobile charge particles, it's an insulator. Right. So then, so this reverse bias mode, if you just think of it, so this region is basically insulator. And then this region is a conductor, and this region is also a kind of very good conductor compared to this region. So then it's like a capacitor. So the capacitor, so the metal plates are here, and this region you have insulator. Now applying higher reverse voltage, you can move these plates towards left. The insulation layer is increased. Now what happens is that this is kind of philosophical, but it's like a capacitor where its capacitance could be varied. So the capacitance is C equals epsilon A over D. Now this remains constant. However, this distance is D is changing. As you change the D, you can change the capacitance. Right? So it's like a voltage dependent capacitor. So when you are in the reverse bias mode, right? So remember that So if you reverse bias something, so the capacitance is increasing, right? That is kind of important. So you should be able to answer question like explain why when PN junction is reverse bias, the capacitance is increasing. So you should be able to answer such questions. Right. So then we'll consider the other situation, forward bias situation. Now the battery is connected in different way. Now by default, the electric field is from positive to negative. So I will label it electric field because of the material. I will label this EA just to make it clear. And now electric field from the battery is from positive to negative. So this is the positive terminal and this is the negative terminal of the battery. That electric field is coming in this direction. E battery. Now, what's the resultant electric field? It's EB minus EA towards this direction. Are you all agree with me? Now, just by increasing EB, what you can do is you can make this positive. So that means you can even kill the depletion region and make charge particle to flow through this region. And so since EA is well known for silicon, it is 0.7. And if EB is higher than 0.7, you can let them move. Disable limitation from others. Right. So if this battery voltage is higher than 0.7 in case of silicon, you kill this depletion region and you allow charge particle to move. So basically you get current flow through this one. But if the battery is in the other way around, you can't let the current to flow. So this basically the PN junction is work as some sort of non-return valve. And this is so it's a model for the diode. So diode is the kind of concept that people wanted to have something. So in one direction, it allows to current flow, and the other direction, it blocks the current flow. So that is the concept people had, and people looking for different mechanisms. And when you have PN junction, it has that functionality. So when the electric field is in the opposite direction, it does not allow current to pass, and in the other direction, it allows current to pass. So this is the beginning of the realization of PN junction, right? But diode. There is a question, sir. When EB increase, it will decrease EA or EA remains constant. Yeah. So that's a very good question. Basically, EA, that's the potential due to the barrier. This remains constant 0.7. But when you apply electric field from the outside, so that electric field is increasing. So the resultant is basically, if this is greater than 0.7, the resultant electric field is coming in the other direction. So this resultant electric field is E battery minus E barrier. So sorry, barrier, it's EA. So this is 0.7, it remains constant, but the resultant one you don't see. Okay, good question. Right. So then, so when we monitor the way it works, so when reverse bias mode, the amount, so this is voltage, right? So voltage applied across this junction. So when it is reverse bias, this current is extremely small. So when we plot this curve, this axis is not exactly just like the positive side. Negative side is it's magnified 1,000 times, right? So it's 1,000 times magnified. That is why you see a small amount of current. Otherwise, this is almost zero. This current is called leakage current, and it's almost zero. And the positive side, it goes like this. It's kind of approximate to some sort of exponential curve. And this is the equation. ID, that's the current through the junction, is equal to IS. So it is called the saturation current. It's a fixed amount. That current into e to the power Q divided by KT into VD. So Q is a constant, that is the charge of electron or the elementary charge. K is a Boltzmann constant, which is again a constant. And T is the temperature, absolute temperature. So the temperature of the junction. And VD is the supply voltage. Right? So depending on this voltage, this increases. So if the temperature is fixed, so everything is fixed. So you are getting some sort of exponential curve like this. And this equation can be approximate to something like this. It's VD is the barrier potential 0.7 divided by VT. VT is this voltage like thing because of, sorry, VD is not the barrier potential, it's the potential that you apply. VT is kind of constant. So basically this VT is this section. It's now here we have e to the power Q divided by KT into VD. Right? So the same thing you can write e to the power VD divided by KT divided by Q. Right? So this section is termed as VT. So sometimes called thermal voltage. And at room temperature, this is roughly 25.9 or 26 millivolts. Right? So it's from this equation, you can explain how diode behaves, but you don't need to remember those things. I'm just telling you just for your knowledge. So this is the behavior. So this one is, I'm pretty sure you already know, this is the well-known VI characteristic curve for a PN junction. And when you make the diode using the PN junctions, this is the characteristic curve of the diode, right? So with that, I'm stopping the section 1 of this series, that is the material, right? Now I'm going to move to another section.
Recording stopped.
Right. So now this section onwards, we are talking about the devices. So the material, like material level questions and things like that, we don't raise here. So we treat this section, we treat them as a component, right? Let me start recording.
Recording in progress.
Now, whenever you see this circuit symbol, you recognize what this is. So this is a diode, right? So this is a diode. Now, remember that diode was a mathematical concept, not a real device. Originally, it was a mathematical concept. So the idea is that, so you can see there is an arrow here. To this direction, it allows current to flow. And when current try to goes in this direction, it simply blocks. Right? So that's the meaning of this symbol. So it's basically a non-written value. Right? So it's a kind of a very simple concept. When you look at the VI characteristics of the diode, ideal diode, the concept, the symbol looks like this. And when it is forward bias, after 0 volt, it should conduct. And when it is reverse bias, it should not conduct. Is it clear, this VI curve? Right. So it's the simplest the concept we call this is ideal diode. Right. So that is the original concept of the diode. Now after that, people start hunting different things and then came up with the idea, okay, why don't we use PN junction as a diode? So we'll come to that shortly, right? Now again, when you look at the diode, when it is forward bias, right? So when it is forward bias, what happens is that ideal diodes, they don't have barrier potential, so they simply conduct, right? So what can you say about the voltage across the diode in the ideal diode when it is forward bias? It is 0. And current through this diode is a non-zero value. So there is a current through the diode, right? And when it is reverse bias, voltage is a non-zero value, but current is 0. So then this one is exactly analog to a closed circuit and open circuit. When you have closed circuit, what is the potential drop across this switch? It's 0 volts, but you have a current. So it's a 0 volt and you have a current, non-zero value for the current. And when you have open circuit, you have some potential difference here, but still you don't have current. So basically a diode, ideal diode, is exactly equal to a mechanical switch, and the reverse bias mode and forward bias modes are analog or equal to or similar to closed switch and open switch. So this is the kind of almost real type of VI curve. So this axis is voltage and this axis is current. So the VI curve, and it usually looks like this, and this one goes a little bit longer and it goes down. Right? So usually, so this potential is what we call the barrier potential, and this barrier potential is 0.7 for germanium, sorry, 0.2 for germanium and 0.7 for silicon. And you can make different semiconducting material like indium, gallium, arsenide. So we can have materials like this with different barrier potential. So light emitting diodes are such devices. Right? And if you have a diode and nothing is mentioned about the diode, you can always assume it as a silicon diode, then barrier potential is 0.7. Otherwise, if it is ideal diode, it is mentioned. If it is germanium diode, it is mentioned. Otherwise, if it is a typical diode, you can always assume it's a silicon diode, then barrier potential is 0.7. So this is the circuit symbol. This is how the PN junction is arranged according to the circuit symbol. And usually with the diode, you will see some sort of line. So depending on the type, it could be a black diode with a silver line or some transparent casing with a black line. So this line is basically your cathode. Right? So this is the cathode, the black line in the real device, the cathode. Right. So then the discussion between the ideal diode and the kind of diode made with the semiconducting material. So ideal diode, it's like this. So you don't have barrier potential, which is barrier potential is 0. It's exactly like a switch. Forward bias mode is like closed switch, open bias mode is like, reverse bias mode is like open switch. The similar model, you can put it here if you just forget about this exponential curve. So when you have the diode made with PN junctions, the forward bias mode starts conducting after 0.7 volts, but after that you are conducting. And reverse bias mode, of course, you don't conduct. So the current is very small. So that looks like this. So you have a like a kind of 0.7 barrier potential you need to overcome. So it's like this, right? Yeah, the same thing. All right. So then I have a few questions for you to fill up. Uh,
Recording stopped.
so
Recording in
basically, I
progress.
have 4 different circuits labeled with A, B, C, D. And what I want you to find is for each and every circuit, what are the potential at these points and what are the current through this one. So you can say so these are like nothing is mentioned. Okay, diodes are silicon diodes. So if it is forward bias, drop is 0.7, right? Okay, now for example, I'll start with this D. So what I can say is current is 0. How about the potential drop here? Or the potential difference in between these 2 points, ground and this point? It's 5 volts, right? Okay, likewise, shall it start with A? What is the potential at point P? Right, right. I'm receiving some answers. Okay, the first of all, when we have diode, first thing that we need to do is check whether the diode is forward bias or reverse bias. Now, in this case, is it forward bias or reverse bias? The diode D1, is it forward bias or reverse bias? It is forward bias, right? So so the way that you recognize is that we have higher potential here and lower potential here. If there is a current flow direction has to be in this direction, right? High potential to low potential. The diode arrow also in the same direction. Okay, this is forward bias. So since it is forward bias, when it's conducting, what is the expected potential drop across the diode? It is 0.7 since it's a silicon diode. So you have 0 here. So what should be the potential at this point? This has to be 0.7 and you drop that 0.7 through this one, you reach 0. Is it clear? Right. Okay. So then current through this one, you can find what is the potential drop across this resistor. It is 4.3 divided by 1K. You get the current. Right. Okay. So the next circuit, circuit B, what is the potential at this point? It is 0 and current through this one is 5 divided by 1K. Right. So this current through the circuit A and current through circuit B, they are almost the same, right? The 4.3 divided by 1K, 5 divided by 1K. And the potential drop here, it's 0 volts. Potential at this point is 0 volts. Here you are getting 0.7. That's slight difference. But here in this case, now what can you say about the circuit C? First thing is, what is the biasing of the diode D2? It's reverse bias. So that means there's no current flows to this one, I equals 0. Almost 0, right? So then what can you say about the potential at this point? Everyone give me the answer. So it's all right, even if it is not correct, that's all right. Just give me the answer. So because there's no current, so there's no potential drop across the resistor. It's V equals IR, right? So you have 5 volts, you get same 5 volts here. So the potential drop across the resistor, diode is 5 volts in this case. Potential over here is 5 volts, right? So this situation, P and D, they are exactly equal, right? So open circuit and reverse bias diode. Closed circuit and forward bias diode, they are almost similar, not exactly. All right. Now do a quick calculation and tell me the answer. So nothing is mentioned about the diodes, right? So assume they are silicon diodes and tell me what this voltage is and what the current through this one for circuit papers.
Recording stopped.
So the current, you can give me answer like some fraction, this divided by this. That's all right. I need current and voltage for circuit tape. All right, good. So it's basically since the diode is forward bias, so you have higher voltage and low voltage here. So this becomes 0.7. So the potential drop across this one becomes 4.3. So the current through this one is 4.3 divided by 2.5 K. Okay. So can you do the same for this one? Current is labeled in this way and this voltage for circuit B. Now, first of all, tell me whether this is forward bias or reverse bias, the diode. You have minus 5 volts, right? So here you have 0 and here you have minus 5. So if there's a current flow, that has to happen in this direction. Diode arrow is in the opposite direction. This is reverse bias. So that directly this answer I equals 0. So then you have minus 5 volts here. There is no potential drop across the resistor because it's V equals IR. I is 0. So that means V is 0, no potential drop. So you have minus 5 here. You get same minus 5 here. So minus 5 here, 0 here. So this is basically, this difference is 5 volts. All right.
Recording in
Now
progress.
take a look at this circuit. This is kind of very interesting circuit. Again, you have assumed that you have 2 silicon diodes and V in voltage, it could take any of these, right? Now let's consider V in voltage is 1 volts. Let me label this diode as D1 and D2. Right, so we need to find V out voltage. Right. So what can you say about the biasing of diode D1? Is it forward bias or reverse bias? Everyone give me the answer. Right. So few of you say it's forward bias. So you have 1 volt here and 5 volts here, right? So if there is a current flow, that has to happen in this direction. So the arrow is in the opposite direction. Okay, this is a reverse bias. So that you can say there's no current going in this direction. Is it clear? Then what can you say about the D2 diode? Is it forward bias or reverse bias? So everyone give me the answer. Right. Most of you say it's reverse bias, but very few say it's forward bias. Now let's take a look at this carefully. So this is connected to the ground, right? So what's the potential here then? It is 0 volts. Now everywhere else, whenever you have power supply, here you have 1 volts, here you have 5 volts, right? If there is a current flow through this diode, or the if you let's say if you don't have a diode, you just connect this one with the conductor. If there's a current flow, should that be towards A or B? Yeah. If there is a current flow, that current flow has to happen in this direction because this is where you have the lowest potential, right? So the current flow has to happen in this direction, but because of the higher voltages over here, current the diode get reverse bias, right? So easier way to recognize is that diode symbol, the arrow is pointing towards this direction. So the diode arrow is pointing towards this direction. And if there is a current flow, that has to happen in this direction. So therefore, this is reverse bias. Is it clear to find the way that I find it? Those who said it is forward bias. Right. Okay. So in other words, this is also reverse bias, right? Now, what can you say about current through this terminal I2? So that diode is there, right? Sorry, diode is there. So I2 is also 0. Now, what can you say about current through this one, I3? I3 current? That it's also 0 because it's open circuit. There's no way of current going in this direction because you need to have a circuit to be completed. So this is also 0. So then what you can say is the current through the resistor is 0, right? Because all three of them are 0. So then what can you say about the potential at this point? It's same as the potential at this point because there's no potential drop across the resistor because of the current is 0. So that you have 1 volts here. From this side, you are getting 1 volts. So it's the same conductor. Right. Okay, let's consider situation where we have the 6 volts. What can you say about D2 diode? Is it forward bias or reverse bias? It is reverse bias, right? D2, I'm talking about D2, it's reverse bias, right? So basically no current flows through this one. Then what can you say about the diode D1? It is forward bias, right? Now D1 is forward bias and potential at this point is 5 volts. And the potential drop across this diode, we can assume this as silicon, it is 0.7 volts. What should be the potential at this point? Right, thank you. Okay, let's consider like we have like basically I'm seeing 3 answers or 4 answers. One is 5.3, 5.7, 4.3, 0.3. Don't know from where you are getting 0.3. Others are kind of 5.3 also. So it's a silicon diode, right? So it's nothing is since nothing is mentioned, you always assume this is silicon diode. Drop is 0.7. Now, so you have 5 volts here, right? So let's assume that we have 4.3 volts at this point. So if you have 4.3 volts and we drop 0.7 here, then what would you expect at this point? It's 4.3, you drop 0.7, you're expecting 3.6 volts, which is not correct. We have 5 volts. Is it clear? This is not correct, right? 4.3 is not correct. Is it clear to everyone? Right. So in order to get 5 volts here, by getting this one forward bias, you need to have 5.7 volts. So let's say we have 5.7 here. Okay, you drop 0.7 through this one, you get 5 volts. So this could be 5.7. Is it clear to you? Right. So then V out voltage is 5.7 in this case. So when you look at this branch, basically you have 6 volts. And here you have 5.7. So the difference happens in the resistor. It is 0.3 volts. Is it clear? And then from that you can find the current through the resistor IR, that is 0.3 divided by 10. Right? So that current, they are not going in this direction or this direction. They are going in this direction. Is it clear to you? Any question to us? Right, okay, good. Thank you. Right, so now what I want you to do is, I want you to do this, plot a curve for this one as a homework. So this axis is V in, that is input voltage, and then this axis is V out. So I want you to find values input and output values. So maybe we'll go from minus 7 volts to plus 7 volts in 0.5 volt step. And I want to plot V out against V in for this curve, right? So you can note it down. It's a homework that you can do. Right? So this is kind of very interesting results. You will get it once you plot it. Right? So those who do this one, remind me to discuss this one next week. Right? Okay. This one I'll leave it as homework. All right. Now, can you find potential at point C?
Recording stopped.
Because all three diodes get forward bias, you drop 0.7 here, another 0.7 here, another 0.7 here. So it's altogether 2.1 volts you drop here, and it's n minus 2.1 is. So you can simply do it like step by step. So you have 10 here, you drop 0.7, so this becomes 9.3. Again, you drop another 0.7, so this becomes 8.6. You drop another 7, this becomes 7.9 watts. So if you want, you can calculate the current if you know the resistor value. Right? So now, what can you say about the potential at this point for this circuit? It's 2.1, right? So all three diodes are forward biased because we have 10 volts and 0 volts. All of them are forward biased. So you have 0 here. This potential should be 0.7. So this potential should be 1.4. This potential should be 2.1. Right. Okay, you have the answer here. Right. So this is kind of very interesting. So maybe I'll make it a little bit simpler. Okay, let me. Right, so I'll use two of them.
Recording in progress.
For this circuit, what I want you to do is to find this voltage. Let's say point F. What's the voltage at that point? And I'll label this as D1 and D2. I'll give you a few minutes to come up with the answer. Then we'll start the discussion. If when you have the answer, just post it.
Recording stopped.
So since you have the diode, so you start with the biasing of those diodes, right?
Recording in progress.
So please help me to get this analyzed, right? So let's start with diode D1. What is the biasing of that diode? Yeah, 3 volts here, maybe ground here. So it's forward bias, right? So when this diode get forward bias, what could be the potential at this point? You get a drop of 0.7, you have 3, you drop 0.7, you get 2.3, right? So then, so here also 2.3, this value is 2.3. Now what's the biasing of D2 diode? D2 diode is reverse bias, right? That is fine. Okay, so let me start asking a few questions in slightly different way. Now let's start the analysis with diode D1. Sorry, D2. Right? So you have 2 volts here and ground here. There's a possibility for D2 to get forward bias, right? If you start here. Are you all agree with me? Right. So let's say D2 diode get forward bias, then what is the expected voltage at this point? It's 1.3, you drop 0.7, you expect 1.3 volts, right? So everywhere in this conductor, so we expect 1.3. Now, when you look at D2 diode, now here you have 1.3 volts. And this side you have 3 volts. What should be the biasing of D2 diode? This should be forward bias, right? So if this is forward bias, what is expected voltage over here is that you have 3 volts and this is 2.3 volts. Is it clear? Right. So now there is a conflict, right? So from one analysis, it says it should be 2.3 volts, and another analysis it says it's 1.3 volts. Now the rule is that in one single conductor you can't have 2 voltages, right? So therefore, both of the voltages cannot be correct, right? So if something like this happens, you need to go back and see what is the situation, right? Now in this case, so either answer A or B should be correct. However, now if this D2 diode is forward bias, you get 1.3, and that by having that 1.3, you can't get the other diode reverse bias. Right? So the other diode cannot be reverse bias. So therefore, 1.3 works only with the diode D2, but it does not work with the diode D. Sorry, this is D1, right? Very sorry, I put wrong one. So this is D1. So the 1.3 works only with D2, but it does not work with D1. Right? However, if you consider 2.3, it works with D1 as well as when you have 2.3 volts here in the conductor, this get reverse bias. Right? So that is also possible. So therefore, we have to reject 1.3 and accept 2.3 volts. Right? So whenever there is a contradiction, now this is what happens now. Let's say you supply 0 volts here and 2 volts here. This get forward bias and this voltage becomes 1.3 volts. And all of a sudden, when you supply 3 volts here, this get forward bias and this get reverse bias automatically. And this voltage becomes 2.3. Are you getting my point? Right. Okay, good. Right. So the analysis. So I just arrange this analysis with the 3 volts. So you will start with 3 volts and you are not getting any issue. But if you started with the other side, it's a different story. The same with the having the third one also. If you start with this one, you get 0.3 volts here. Then with the 0.3, this diode get forward bias, but when it is get forward bias, you expect 1.3 volts. Then 0.3 and 1.3 cannot be exist, so you have to accept 1.3 is correct, so this get reverse bias. Then again, when you argue with this one, you have to reject this one and 2.3 becomes the correct answer. At that time, all three working perfectly. Right? Those who want to get the repeat, so recording is there, right? So I will upload the recording. Right. So this one is also kind of similar, but let's see this one also. Let me remove one of them so that it's kind of easier for you. So I'll remove C. Right. So now the voltage over here is 0 volts. B is 5 volts. So the question is, what's the voltage at point F? Can you try to find it and post it in the chat window?
Recording stopped. Recording in
So let's
progress.
consider diode D1. What's the biasing of D1 diode? It's forward bias, so that since you have 0 volts here, you expect 0.7 volts here. So with the 0.7, you have 0.7 here and 5 volts here. What's the biasing of D2 diode? It's reverse bias, so it's acceptable situation. So this is 0.7 volts. Right? Yeah, this one is more or less the same. You can you just fill this table quickly?
Recording stopped.
So when you have 0 and 0, both diode get forward bias, right? So what should be the voltage at this point in this case? 0 and 0, it's 0.7. I'm seeing some answers like 3.5. It's not, there's no rule like you are dividing or anything, right? So when this one forward bias, you have 0 volts here, you get 0.7 here. So same 0.7 exists in the conductor, 0.7 and 0, this also get forward bias. So then system agrees. So basically this becomes 0.7. Right? Then when you have 0 and 5, just like the previous case, so it's a 0.7. This one also just like the previous case, it's also 0.7. But when you have 5 volts and 5 volts, it's slightly different. Now you have 5 volts here, 5 volts here, 5 volts here. What's the biasing of diode A? The biasing of diode A? Yeah, you can say it is reverse bias. It's zero bias, but zero bias situation you can consider as reverse bias, right? Diode B also reverse bias. So in that case, you are not draining any current, right? So this current becomes zero. Are you all agree with me? So then the potential drop across this resistor also zero because there's no current. You have 5 volts here, you get 5 volts here. Is it clear? Right. So now remember that in digital electronics, for sure, you will learn this one. Now in digital electronics, we have something called TTL logic, transistor logic. Any voltage in between 0 to 0.8 volts, we consider this as logic 0. And any voltage in between 3.5 volts to 5 volts, we consider this as logic 1, right? So this is like you can consider as a truth table. So in blue, I will put, so this is logic 0, logic 0, logic 0, logic 1, 1, 0, 1, 1. And what is the logic value for this one? 0.7. So that is 0. 0.7, 0, 0, and this is 1. Right? So this is, you can see the logic value. This is the truth table for O gate. Oh, sorry, AND gate. Sorry, AND gate. So AND gates, you can make it like this. O gates also, you can make it using diodes. So this is a 3-input O gate, basically. If you do the analysis just like that. Yeah, you can fill this one as a homework, right? So I expect you to fill these ones and get things done so that you will have a better understanding.
Recording in
So this is
progress.
kind of very interesting circuit. In fact, there is no difference between, let's say, this circuit, if you have just 2 inputs, and this circuit, right? So that we have like 2 different power supply and put into a different context. So the same circuit, I can draw it like this if you want. You have 2 diodes connecting like this. And here you have the output, and here you have resistor. So the resistor is this your wall clock, and then you have voltage source that is 15 volts, and the other one is 12 volts. So it's exactly like that, right? So let me explain this one. So here what you have is a wall clock, which is capable of running by supplying any voltage between 10 to 15 volts. And then here you have a car battery. So this is positive terminal and negative terminal. And here you have a 230 volts AC to 15 volt DC converter. Whenever main supply is present, you are getting 15 volts here. Right? Now, let's say we have the main supply. What is the biasing situation of D1 diode? It gets forward bias, right? So then what's the expected voltage here? It is 14.3. Now, if you have 14.3 in this conductor, now is it compatible with diode D2? Now, what is the biasing of D2 diode? It is reverse bias. Okay, it is compatible and having 14.3, so it is in between 10 and 15, this works. So when main supply is present, you are getting 14.3 volts and this device works. And now what can you say about the current taken from this diode D2? It is zero because D2 diode is reverse bias. So you don't take any current. When main supply is present, you don't take any current from the battery. Okay. Now let's see a situation where the main supply is failed. So you have 0 volts here. So in that case, what can you say about the biasing of D2 diode? D1 anyway get reverse bias, right? Because you have 0 volts. So some voltage will come here. So this becomes reverse bias. So D2 becomes forward bias. Then what is the expected voltage over here? It's 12 minus 7, that is 11.3 volts. So then this device is capable of running it. This is reverse bias. So everything is fine. Now, what can you say about current going to the main grid from the system? I1. No current flows in this direction, right? So in other words, what's really happening here is that when main supply is present, diode D1 works as a switch which is connected. And at the same time, this switch is open. When power gets failed, so this one simply break the circuit and become open circuit, and this one get connected. See, now this is one of the real interesting application where you can use diode as a switch. So when main supply is there, you connect the switch. When main supply is there, you break the circuit. So that it simply supply it won't take current from the battery, and battery won't discharge as long as main supply is there. When main supply plays, automatically it transfers, and this transferring happens really fast, and the clock will not even notice it then. Right? It's kind of very interesting circuits. I just got it from the Art of Electronics. Right. So again, the characteristic curve. So silicon and germanium. So silicon, your barrier potential is something like 0.7, and germanium it's like 0.2, right? Yeah, we have seen this one, right? And the temperature dependence. So this is something important to understand. So we discussed this parameter, right? VT is KT over Q. So as temperature increases, VT increases. So when VT increases, basically this divided by this whole parameter decreases. So for different temperatures, you can see different VI curves. So if you remember it carefully, then temperature increases, VT. When temperature increases, this one increases, the whole thing decreases, the whole thing decreases, right? So when you at 25 degrees Celsius, it's like this. But when temperature increases, so it goes like this, right? So it changes the curve. And this is kind of interesting. So you can theoretically calculate this change also. So this IS current, right? So this current is roughly doubled every 10K rise temperature for reverse bias mode. So you don't need to worry about too much of this one, but remember there is a temperature dependence, right? And so this one also temperature dependent parameter, although it's a constant, it's not really a constant. So that's a complex effect is there. So it's out of our course scope, but remember that temperature variation effect to the system. So that is the main thing that you need to understand. And also you should be able to explain that also by considering whole electron pair generation and so on. Right. So a few terminologies coming again. The bias, we discussed already this one. It's a supplying some voltage or current to a different points of the circuit. Right. So if it is diode, so if we apply voltage in with a certain polarity, we call it forward bias. But if it is in the other polarity, it's called reverse bias. Okay. So then we have a quotient point or the operating point. That's the optimum bias, which guaranteed the proper operation of the device, right? So the Q point, we need to fix it to a certain level, that's operating point. But Q point, you need to make sure that Q point is like different voltages and current values, right? So, then there is a graphical way of analyzing circuit called DC load line analysis. We'll take a look at the load line analysis circuit and see how to get this done, right? Now consider this circuit, what you see on your left. Right? So you have a voltage source V1, a diode, and a resistor, right? So in load line analysis, what you could do is you need to find now remember that diode is a kind of nonlinear device, right? So the nonlinear in the sense that if you consider VD against ID, the curve goes like this, right? It's not a line, it's a very complex curve, kind of exponential curve. So when you have nonlinear devices, if you want to analyze how system works, one of the easiest ways to get it done using load line analysis, right? So this one is extremely simple circuit, and from this one you can find it, the exact voltage where it operates, right? Now, what we usually do is you apply Kirchhoff law, Kirchhoff voltage law to this circuit. So we can apply it to this loop and find the current through the diode. So this is ID. So you can simply write, so it's V1 equals potential drop across the diode. Let me write it as VD plus a potential drop across the resistor, that is ID. So it's the same current flows through the resistor, RL. So then if you want to write ID you can write it's V1 minus VD divided by RL. Right? So this is one of the equations where you can use to plot the load line. Now remember, okay, so I didn't explain one thing here. Now for you to do the load line analysis, what we do is we'll take the diode characteristic curve. So we remove diode from the circuit and see how it behaves, right? So this is what we have plotted here, right? So the black curve is basically the VI curve for the diode. So the x-axis is voltage across the diode and the y-axis is current through the diode. Is it clear, the first step? Right. So the second step is that you see the effect from the circuit to the diode and find this relationship between diode current and voltage somehow, right? So for this one, we apply Kirchhoff voltage law and we came up with this one when you in the circuit, right? So the black curve, what it says that if you have certain voltage, this is the current that can have had. If you have another voltage, this is what you can have from the diode itself. Diode can't have anything else, right? So that is what that curve says. And the second one says what system allows, right? So the diode is now in a system. What system allows? So that is what we did with the Kirchhoff voltage law. We found this one, right? So this one is basically, you can see, so basically what we need to, so I can rewrite, so it's VI divided by RL minus VD divided by RL. Yeah, that doesn't help a lot. So anyways, so this is so when you remove diode from the system, it's a linear behavior system has, right? So, but the effect from the diode coming up here from the voltage, right? So that's what we have mentioned here, right? So then what we do is we draw this, what do you call the load line? The load line is the system behavior if you forget about the nonlinear behavior of the diode, right? So in this particular case. So then for this particular equation, you can consider what happens when VD equals 0. VD is the voltage across the diode. So when VD equals 0, ID equals, so this is 0, it's VI divided by RL. Okay, so this is VI divided by RL. That point, right? So this point is basically 0, comma, this value. And then again, we consider situation where ID equals 0. So the current through this one, if it is 0, then if ID is 0, basically this is 0. So then this equals this, right? So VD equals this one. So that point is this. So it is V1, comma 0. That is the point. Is it clear what I'm doing now? Right. So this is the load line, right? So what load line says is, so the red one is the load line. Load line says, if you don't consider the behavior of the nonlinear device, how system behaves, right? So then we get the intersection point, that is the agreement. Now diode operates, so note that this is VD, right? This is VD and ID. So in both cases, we are plotting the potential drop across the diode against the current through the diode. So the red one and black one both agreed at this point. And this point we call Q point, or the quotient point, or the operating point. For this particular circuit operating point, you can simply find what the voltage and the current is. Right? So this is a graphical way of finding it. Right? But in order for you to get this done, either you should be able to plot this one, or you should know the equation for this curve, that model, that exponential model, so that you have two equations, you can solve them and find the voltage and current for this operating point. So one way to get it done is the graphical way, or else you use these two equations and solve it and find it, the Q point, right? So now this here, we don't just assume that when diode is forward bias, it is 0.7 volts. Right? We don't just assume that. So what we do is we use this curve, and because it could be any voltage. So if we are operating here, it could be like 6. So if it is here, it could be like 7.5 or something like that. But when you do this one, you can find exact operating voltage. Is it clear to everyone? So this is a method to find the exact voltage, right? So this is called the load line analysis. Or else you can simply do, you can use another model called constant voltage model. So that is what we do, right? So when you have a circuit like this, if you want to find potential at this point, what we simply do is, okay, we have this voltage, drop over here is 0.7. Okay, find the answer. That's it. Right? Even for this one, if you want to find the potential, you can simply use the constant voltage model. So that is what we do. Right? So when you have a circuit like this, if you want to find potential at this point, what we simply do is, okay, we have this voltage, drop over here is 0.7. Okay, find the answer. That's it. Right? Even for this one, if you want to find the the operating point, basically this is 0.7. So this is 0.7 volts. This voltage is 0.7 volts. Our traditional approach, right? So it's a 0.7 volts. And then the potential drop across this one is V1 minus 0.7 divided by the resistance. RL, you get the current through this one, that is ID. You get ID, which is not correct for sure. Right? Because when you assume that the potential drop is 0.7, it's not correct always. Right? If you really want to find the exact way, you need to go along with this load line analysis. Right? But in most of the cases, we don't do this one. We just assume, okay, this drop is 0.7 and we use this. That drop 0.7 model is what we call the constant voltage drop model. Right? So that is what we did in all the analysis we did in the morning. Right? So this one is just giving you a slightly different idea if you really want to find the exact current and voltage passes to this one. Then there are like other models also, like you have some sort of piecewise linear models you can use. Like, because that one, when you have the complex curve, the exponential curve, it's very difficult for you to handle it. Then there is another model called piecewise linear model. So your curve looks like the one over here, but this piece you say, okay, it works like this, the rest is another line. So piecewise linear is that you have curve like this, so, but you are fitting pieces of linear curves. Okay? So there is a model that you don't need to worry about that, but that model also you can use it. So that is what you do with the mathematics, right? There are different ways to get things done. Now, when you use piecewise linear model, it's not exactly as correct as the exponential model, but it's much simpler and easy to solve it. But the accuracy also pretty high compared to the constant voltage model. Okay. I will finish with the peak detector. Now, this circuit is kind of very interesting circuit. Right? Now, what you have here as the input is you have some sort of signal. It's a voltage. It varies over the time. But let's say you are taking some measurement and you need to detect what the peak voltage is in the system. We don't know. We are taking some measurement. So probably it's some voltage coming from a temperature sensor. So we just keep on measuring it, but you need to record what the maximum temperature happens in this system. Right? For that, you can use this circuit, right? This is kind of, so this one is this one. Right? This circuit is kind of very interesting. You just have a diode and a capacitor. Now, let's say if you are now let's say your signal looks like this, and this is T. This is the voltage, right? Let's forget about this signal. I'll come to that later, right? Let's say our signal looks like this. We need to record the maximum voltage that is present in the system. Let's say we have a peak like this, and we need to know the peak voltage. Now, let's say if our voltage is somewhere here. So initially, let's assume that capacitor is charged to 0, right? So potential here is 0 initially. Now, when you at T equals T1, you get some voltage V dash, right? So this voltage is V dash. Then what is the voltage that you expect over here? Okay, V dash is greater than 0.7. Sorry, I did mention. Okay, what's the potential that you expect over here? That is V dash minus 0.7, right? So this one get forward bias with the drop of 0.7, you get a voltage of V dash minus 0.7 volt. Now what happens is that this capacitor gets charged to this voltage, right? because you don't have resistor, it's suddenly charged to this one, and this potential remains there. This one. Now, let's say now after a while, like t equals t2, you are going to go to V2 voltage, which is higher than that. Now this voltage is V1 and this voltage is V2. And then again, this one get forward bias so that the capacitor charges again to new voltage, that is V2 minus 0.7 volt. So once you reach the peak at t equals t3, you reach the peak, let's say Vp, then this voltage is Vp. What is the biasing of this diode? Diode get forward bias and this voltage becomes Vp minus 0.7 volt. Is it clear to you? The capacitor charged to that. Okay, now let's consider a situation where it is going down. Let me clear this area a little bit. Okay, now let's consider now a voltage. The time is here, T4. Voltage is V2, right? Now input voltage is V2. Now what is the biasing of diode? Input voltage is V2. Capacitor is charged to this voltage. What is the biasing of diode? Diode gets driven bias because this voltage is larger compared to this voltage. So therefore, whatever the voltage you are coming here, this diode get reverse bias. Then what can you say about the current through the diode when it is reverse bias? It is zero. That means capacitor will not discharge. Are you getting my point? So capacitor will not get discharged. Now what happens is that although the voltage goes to zero here, this capacitor is charged to a voltage that is peak voltage minus 0.7. So that you can simply detect the peak. Is it clear how do we detect the peak? So if you really want to see the peak voltage, you measure the capacitor voltage at 0.7, you get the peak voltage. So again, in this case also, diode works as a closed and open circuit. So I'll take one more minute, although my time is exceeding. Now, let's say you have something like this signal. So still, you can see the if you apply this kind of signal here, you will see this peak voltage. Finally, you are seeing over here, right? Although it's charged here, then here it is reverse bias again. When you are going above this one, again capacitor starts charging, then capacitor charges to the maximum voltage minus 0.7. When you are going down, nothing happens. The same thing, right? Okay, so with that, I'll stop today's session. So thank you very much, everyone. So you can log out and go. There are a few homework activities I have given. Please do them. And also the questionnaire that I have, quiz that I have given, please do it again. So that will really help you to improve yourself.
Recording
Thank you
stopped.
very much. Please go and log into the next one. Do we have the next session? Next session is by whom? Is there a message or anything that says it's cancelled? Or? Yes. We'll, Yeah. Last time the lecturer was like not well, so he will do. He will do the classes. So just try to log and see, right? Okay, thank you.